Ladies and gentlemen, this is Alice in Beijing. I'm so glad to meet you on the Friday evening. I can act talks, connect the world and the universe. We are so proud, to have all of you every Friday to meet on this global online talks. I can act talks is a new kind of global online talks for the science and technologies. Every week, we invited the top scientists from worldwide to deliver their research, the latest result, and to share with all of you. So I can act talks is a new thing. It's a talks for science. It's a talks for technology. It's a talk to try to connect you and me in the universe. So I can act talks has got a lot of attention on this, and everyone knows that we are so proud, to have to be one part of a global open talks for Peking University. At Peking University, everyone knows that's a world leading university, and they have host a new event, the Global Open Talks. These talks short as Excellence. We invite scientists, socialists, artists, and all this to get online to give talks. So I can act talks is one part of Global Open Talks for the technical part. So in last few weeks, we got, 5 weeks, we got 10 speakers on ICANN Talks stage. So all of them from a different place, and they deliver very nice talks. So we name that as, some Superman was fighting on the stage to show the latest results. So it's a lot of, new things to come out. We're proud of that. We have all of these top scientists here. And we not only have the top scientists to deliver the talks. After their talks, we have the students volunteer, from different places, different universities to write the technical report for all these talks. So this was contained for 5 weeks. Every speaker on these stages, you will have a very detailed, very nice technical report. So we name as Global Science Talk. Excellent, technical report. We want to share with all of you this latest technology. We want to get more people, to love the high tech. We want to make the science as fashion. We make all these scientists as superstars. So all these students, the volunteers, they did a wonderful job. So if you are interested in this technical report, please scan the code and you can get the report. It's very pretty work. It's very helpful for you to understand all this work. This will continue to get on this ICANN Talks series. So every week after the talks, we will deliver the technical report. So please keep follow us on this. And after this, we have the Twitter for ICANN Talks. So if you are not in mainland China, in the overseas or any other countries, you easily to join us, to follow us on Twitter, ICANN Talks. You can look at all this, watch all these videos replay on the YouTube. Also, just search for ICANN Talks. You can find all these videos. Now, for better help, for better understanding of what you want, we have an online survey. So you can scan the code, or you can, easily to find on the Twitter account for this link, how to, do the online survey. We really need your feedback, because your feedback will, help us to get more good service and invited the right speakers, in the right topics, and to do good things for all of you. So please, remember, do this online survey and follow us on Twitter by ICANN Talks, and watch the replay of all these videos and YouTube. So this week, as normally, this week we have 2 speakers. The speakers will be the same. The special topic this week is really a magic, because they will talk about magical wood science. Normally we think, the science is something always, high tech, but wood, how to do with wood for this science. But, this super scientists, they made not only the wood as such. It make like magic. You can deliver and train all this wood into different kind of skills and make really strengthen and make some special functions. So if you have any questions for this magic wood, so please post your questions in the meeting room, or if you couldn't access it with a meeting room message functions, you can ask a question on Twitter. So on Twitter, and I can ask talks, we will pick up the questions for you too. So please remember, ask the questions. We love to, get more questions and get more interactive with the scientists. So the magic wood science is today's topic. So the first speaker get on the stage is one very interesting speaker. His name is Liangbing Hu. He's from Maryland University. So he really magic because he chose a special topic of wood, and then he made so many different types of wood as science. So I published a paper on science on nature and get a lot of attention on this. So Liangbing, the word is yours. Please share your screen. We're looking forward to your wood nanotechnologies. Liangbing, please.
Thanks, Alex, for the very nice introduction. My name is Liangbing Hu from Hubei, Jianyi, China. It's my great pleasure to have this opportunity to share our research related to on this wood material. It's a very common material. It's a very old material, but we're trying to find new opportunities when we look down at the nano scale. So I also have a startup company called Invent Wood to commercialize the technologies we invented at the University of Maryland. So I would like to take this opportunity to first introduce my research group at the University of Maryland, which is actually at the Washington, D.C. area. So I also welcome... Yes?
Please share your screen. We couldn't see your screen.
Oh, I'm sorry. Sorry about that. Okay, can you see the screen now?
It's coming. Yeah, let me see. Almost. Yeah. Here comes. Please.
It's maximized?
Yeah.
Is it a full screen?
Yeah, it is. Go ahead.
Okay, good. Okay, sorry about that, Alice. Again, thank you very much for the introduction. I would like to take this opportunity to introduce our work related on wood nanotechnologies. So first of all, I would like to take a few moments to discuss my research group overall research. I'm leading a group focused on material innovations and manufacturing. And I personally strongly believe, these days, new technologies always come along with material innovations. New materials very often can enable new technologies. And very often after the material innovation, there's a manufacturing challenge. So I spent a few years in Silicon Valley working for a startup company doing rotary printed electronics. Basically, to take the nanoscale material like carbon nanotubes and make them into inks, and you do this rotary printing for flexible, low-cost electronics. So because of that research experience, very often I take a manufacturing aspect into my research portfolio. So currently, my group is working on 3 major research directions. The first one is called wood nanotechnologies, which I will elaborate today. And we treat wood or cellulose as a new material platform, and to engineer this material to tailor the optical, mechanical, ion transport and fluid behaviors in these wonderful materials. And particularly, we are looking into the nanoscale behavior, and we are looking into the new possibilities of this old material by studying in a new region of this hierarchical structure. So the second research my group is doing a lot is about the batteries. And we're very fortunate to choose the right topic, I believe, is about the solid state batteries. And using ceramic electrolyte instead of organic electrolyte, we can potentially address the safety and energy density aspect at the same time. Very often we will increase the energy density of a battery, and the battery material, the battery device itself become potentially more dangerous because you have more energy in a very small volume. If you have a fire because of the organic electrolyte, you have even more severe consequences. And the last aspect my group is working on is called manufacturing. And I'm very proud of this new research direction. We started about 5 or 6 years ago, and we invented this process called extreme high temperature, thermal shock. By turning the duration of this high temperature process, we can make all kinds of very interesting materials. Yeah. So the logic is very simple. Yeah. So when you're trying to make new materials, right, you want to make it fast. The easiest way to increase the speed is to increase the temperature. So for example, if you increase the temperature from 500 to 3000 by 6 times, you can increase the reaction rate by more than 10 million times. So that if you have a reaction, for example, if you're trying to make a glass window that takes about 10 hours to make, you could potentially make it within a second if you do everything right. So we are actually exploring this new manufacturing platform for new material discoveries. And because it's very fast, so you can potentially manufacture it in a very rapid scale. So I don't have time to talk about this research topic today, but hopefully in the future we have another opportunity to share this this research portfolios. Yeah. So today I'm going to focus on the wood nanotechnologies. So if you look into the future, mankind is going to face a lot of challenges as we're facing right now. This COVID-19 situation, right? So we need to be prepared for the future, right? And if you look at the challenges in the coming future, in the short-term or long-term futures, sustainability is going to be one of the top in the list, right? Sustainable development and climate change, as shown in this chart, is the number one thing, along with clean water, energy, health issues, and so on. So address all these sustainability-related challenges, we have to use materials that potentially have this sustainability feature, right? So then if you look around, there are two kinds of materials. The materials that are made by nature, like leaves, Jino is going to give a talk, plants, all this material that are made by nature every day. And they are biodegradable. That's one of the key feature of this category of materials. And the other category of materials are, human-made materials like steel, glass, and usually they have very poor, they exist in nature for hundreds of years. It's very hard to, to get them completely disappearing. And not to mention plastics. That's another major problems. Right. So for sustainable materials, I think one of the most abundant material is cellulose, and that exists in all kinds of trees, plants, and bamboos, as Alice was mentioning. And on average, in China, a person has about 100 trees. Okay, in US, it's about 700 trees. In Canada, it's about 9,000 trees. Yeah. So globally, on average, we have about 400 trees per person. So now it's really about how can we use this material, right? So now if you look at the tree, just if you stand in front of a tree and look at it, and this material is an anisotropic structure, means the tree grows at a certain direction. And if you zoom in further, you see these interesting polar structures, right? You have these tubular materials. You can see the channels here, right? And these tubular structures are glued together by this so-called lignin, right? It's like a glue. And that's actually why you have this wonderful mechanical properties, the fluid transport properties in trees. The trees can grow in a very large height, right, without breaking it up, even doing very large wind blowing to it, right? So, and people know this material for thousands of years, right? And if you take the lignin away between the tubes, you get these pulps, the paper pulps. And that's actually what the building block of this paper, right? And it's completely white, has very good mechanical properties, flexible, very good for printing because of this porous structure. It's tubular structure. It's hollow in the very center, right? So that's how far we have, be using these materials here, right? There has been a lot of development in the nanoscience and nanotechnologies, and people are always looking for nano materials for enabling new technologies. And I was very, intrigued by the structures of the cell wall, right? If you look at the cell wall of these big tubes, okay, now you see these tiny, tiny nanofibers with a diameter of about 5 nanometer, okay? So that used to be very exciting when you see that, yeah? And they are partially aligned. And if you look into the structure even further, right, it's just like you keep tuning the fiber, okay? If you have a magical hand, okay, if you keep tuning it apart, you will see the fiber itself is made of even smaller fibers, and ultimately it's made of these glucose chains, okay, with a length up to 1 micron, with a lot of hydroxyl groups on the surface. And as I said, this cellulose has a very long molecular chain. Is a molecular weight is very, very large. It's a macromolecules, right? And you have the lignin. The lignin itself is much smaller, the same as hemicellulose. So I'm a physics by training. I don't know this material at all. When I actually, got to know this material, I was more interested in how to use this cellulose fiber as a building block instead of the very complicated chemistry of lignin and hemicellulose. So my research really focused on the cellulose fibers using these materials. And we hope that by doing engineering, we can really take advantage of nanoscience and nanotechnology and using this cellulose nanofiber as a platform. Everything else keep the same, right? So just like many other material-related technologies, there are two ways to process this material, right? So one is called bottom-up, the other one is called top-down. Yeah? So for the bottom-up approach, you have to get these nanofibers. As I said, you can get this nanofiber from wood, from grass, from bamboo, from sugarcane, and so on. Yeah? And typically we use this so-called pulp fibers, right? This is a big fiber, right? So we have to break them apart. We have to tear them down into this nanofiber. We have two major steps. One is chemical approach. The other one is mechanical approach. So chemically, you functionize the hydroxyl groups, the OH groups on the cellulose fiber, and you charge them up, okay? You put a charge on the surface. So by doing so, they will start to repel each other. They will start to hit each other, right? So they will start to push against each other. And then you follow up by the mechanical beeping, okay? You basically throw this pulp into like a wall, okay? Using this mechanical force to break them apart. So now in that case, you can get this wonderful cellulose nanofibers. It's like a gel, okay? It's now become very transparent because the diameter is very, very small. It's only a few nanometers. And remember, this is one of the most abundant nanomaterials, right? And it's actually a very cheap research. I do this research when I, became an assistant professor at the University of Maryland about 9 years ago. It's very cheap, yeah. So I think everybody can afford this kind of research, yeah. And you can literally just cut a tree and you can start to host everything. And I learned this material from Professor Lars Warburg when I was still a postdoc at Stanford University with E-Trade doing the battery research. We're trying to use this material for batteries. And there are a lot of development of using this cellulose nanofiber, and we have done a lot of work such as transparent nano paper, nanocellulose batteries, and so on. I won't have time to discuss today. And when you use this nanomaterial, even though it's very cheap, we did find a lot of potential challenges, right? Just like any other nanomaterial, it's very hard to process it. One of the major reasons is because we need to use a lot of water. Like for example, in this gel, it's about 98% is water. So that means, even though the material is cheap, it's very abundant, the use of the water and the energy to break them down is going to be very expensive, right? So about 5 years ago, I started to think about, what are the potential manufacturing routes to address these issues. And as we look into that aspect, we found out the manufacturing research actually guide us to look into the anisotropic feature of wood. And by doing so, we get actually more opportunities. For example, this is a piece of wood, is a complete 100% of wood. Okay, there's nothing embedded inside. There's no dye, there's no color, fillers, and so on. And we get all this aligned cellulose fiber inside this so-called nano wood. And now you can imagine, you can tailor the channel length, you can tailor the optical properties, you can tailor the fluid transport, and so on. I think this becomes a new platform here. So today, I'm going to give you 3 examples, not a big deal, just 3 examples about how we engineer wood, okay? And I personally believe by using this top-down approach instead of a bottom-up, means you use nanofiber and build up things. Top-down means you use the wood and you don't change the wood and you do things within the wood, okay? Changing the lignin, changing the hemicellulose, changing the pores, blocking some pores, and so on. And we find there are a lot of very interesting, physics behind it, and associated with all this, structures and the physics, there are a lot of potential applications. So the first work is about lightweight structures, and I done this work through very close collaboration with a very good friend, Professor Ten Li at the University of Maryland, in the mechanical engineering department. Now let's look at the mechanical property of paper or wood. It's actually very boring. I mean, mechanical property of paper is about 20 to 60 megapascal. And it's good for printing paper, but you're not going to build a building, for example, or a car using paper. And the wood mechanical property is almost the same. Yeah, it's like 20 to 60 megapascal. It's good for some of the buildings, but you're not going to use it for the skyscraper, okay? Or you're not going to use it for lightweight cars as a frame, right? That's because the 2 features here. One is that you have this very big, building blocks. That's about 50 microns. But the second thing is that you have these very porous structures. The porosity is almost about 50% in either structures, right? So, but at the same time, remember, these big fibers here is made of many, many smaller nanofibers. And the nanofiber is with a diameter, if you zoom in, the nanofiber is with a diameter of about 10 nanometer. And the strength is about 7 gigapascal. The best steel, the strength is about 1 to 2 gigapascal, right, in your car. And the best carbon fiber, the strength is only like 4 gigapascal and most 5 gigapascal. And many people are trying to develop new technologies to replace steel, replace carbon fiber. And this material, made by nature every day, is with a strength up to 7 gigapascal. Okay, and at the same time, this is not by the primary bond, like a mechanical bond as in metals, which takes forever to decompose if you put it in nature. Right? This is actually made with hydrogen bond. The hydrogen bond energy is very, very small, each one. But you do have all this hydrogen bond everywhere. You have about 2,000 hydrogen bond, per molecule change per micron. And because of that, each bond can be broken. So that means this material is very strong. But if you put it into nature, with the help of the sun and water, this material can be decomposed. So this actually gives you a very good combination of excellent mechanical property and biodegradability. So it's very good for your use, and it's very good when you're trying to dispose it. So that's another very important feature of nanofiber. So now, let's say if we want to use this nanofiber, what do we do? So we have to have to break them apart, right? So we've done 2 kind of scaling behaviors. One is with diameter, So this actually was done by Hongli Zhu. Now he's a professor in Northeastern University, Boston. So we were able to break the fiber down to the smaller and the smaller scales and make a paper again, right? So make all kinds of papers using these bigger fibers, smaller fibers, and the smallest fibers, right? And we do this stress strain test, and we can get this ultimate tensile strength when this material start to break. And we found out this mechanical strength indeed follow this kind of quasi-Hall patch related equations, means increase decrease the diameter of the fiber, you increase the mechanical strength dramatically. You can almost increase the strength by up to 100 times because when you decrease the diameter of fibers, you have less defects, the material become much denser. If you have a big fibers, you have limited interaction bond, contact areas. And if you decrease this diameter, you have more interaction rates and you have small defects and so on. So the other thing is the toughness or the energy to break this material, right? So you do the integral of this curve under the stress strain curve, and you get this toughness. Yeah, and we found the toughness also increase as you decrease the diameter of the fiber, and this is untraditional. Because for the steel material, for example, the way to increase the strength is to change the processing, time and the cooling rate. When you cool it faster, you have smaller grains, you have increased mechanical strength. Yeah. But by doing so, you actually sacrifice the ductility and also the toughness. But in this material, we can increase the mechanical strength and the toughness at the same time. Yeah. This is very often very likely due to the fact that this material is made of hydrogen bond, right? The hydrogen bond, each one is weak. So when you break it, because it's very weak, so it has a potential to be reformed. So instead of break, right away for good, they can be reformed with an adjacent hydrogen bond. So this material is not broken right away as you pulling this fiber apart against each other. So we also studied another kind of scaling behavior is the alignment, right? So you know that if you try to increase the mechanical property of fiber materials, when you have certain contact points, the contact point gave its mechanical strength, right? If you align them, you maximize the contact area, you can increase the mechanical strength. So this indeed happened. We carried out this research using this bacterial cellulose fibers. And we stretch them when it's still wet in water, and we take it out and we dry it, right? And then the hydrogen bond will be formed, and you have this increased mechanical strength up to even 1 gigapascal. Okay, so this is actually better than many of the steels using this cellulose, the bio-based materials. We published this paper quite a few years ago. And remember, this material, so this shows you that if you have a random behavior, a random arrangement, this is a mechanical property you have. If you have alignment, you have this kind of much improved mechanical strength. The same thing is actually for the toughness. So now we know that in order to use these cellulose nanofibers, we want two things. We want the nanofiber. We want to use them as aligned fashion, right? And come back to my original point, we always have manufacturing challenges. And for any technology to be useful, you have to overcome the manufacturing challenges. So if you use nanofiber, using the bottom-up approach as I presented in the previous two cases for the scanning behavior, either using alignment or using a microfluidizer to break them apart, that use about 98% of water. And that's a lot of energy associated with that. So remember, cellulose very often come from trees, right? And they are actually partially aligned. Wood tree is actually an anisotropic structure. They grow at certain directions. And the building block is cellulose nanofibers. So we are very lucky to propose this concept quite a few years ago. We have a patent on this. Is that let's use nanofiber as they are in wood. Okay, but let's try not to follow what the paper industry is doing. In the paper industry, they take the wood, they cut into small pieces, and they do this pulp treatment, right, to remove the lignin. They have to cut them into very small pieces so they get a very good diffusion of the chemicals to take the lignin away. But in this case, we want to use the structure, this anisotropic structure. So in this innovation, we remove some of the lignin, so the wood itself becomes soft. At the same time, we apply mechanical force to break them down, right? So by doing so, mechanical force to break down the channels, you have this densified structure. So by doing so, you have all these aligned nanofibers inside, and they are aligned. So we indeed get actually much better mechanical properties, and at the same time, the whole structure is with a density of about 1.3 and 1.6, 1.5 gram per centimeter cube. It's much denser than the regular wood, the starting wood, but the density is still 6 times smaller than most of the steels, right? So this is actually what happened in the laboratory. It's actually very simple. Yeah, you just take the wood, you just cook it using chemicals, using some temperature, and the wood will basically the lignin, just like you wash your cloth, the lignin will be leached out, right? And the wood will be soft, and you press it using actually not much pressure, about 5 megapascal, right? And again, during the drying process, the hydrogen bond formed, and you have this very strong tough material. So this is actually what happened in the laboratory. Again, just like wash cloth, right? So what's happening here is that we're using this sodium hydroxide, right? This is the lignin building blocks. It's actually a very complex amorphous structure. And in one case, right, they can actually introduce these hydrophilic groups. So that means this material will start to like water and it can dissolve into water. In the other case, you can use hydroxide groups to break this kind of acyl group, right? You can break down these very large macromolecules of lignin into small molecules, right? When they are small, they are easier to leach out, to actually dissolve into the water, and you can remove the very rigid lignin, right? So this is actually what happened on the composition studies. And this is lignin is, about 50% of the original lignin. And the cellulose in this case still, remain most of the original mass. That's what we wanted. We want to use the cellulose. We don't want to use the lignin because they are causing problems for densification, right? So we do this mechanical stress strain test, and this is the natural wood. This is the densified wood. So you can see the tensile strength is increased more than 10 times. The toughness is also increased about 10 times. Because this material is very lightweight compared to steels and even the best lightweight metals, the specific strength of this densified wood is actually significantly better than titanium alloy lightweight metals. And if we look into the structure, you see this is a natural wood, very big channels. They are actually defects from mechanical point of view. And you see how actually the cell walls are wrinkled and lock each other, form a very dense structures. And if you look at the very nanoscale, you do have this kind of alignment that maximize the interactions between the building blocks. And we've also done a lot of other kinds of tests, such as bending. You bend in different directions. You increase by a lot in compared with the natural wood. For building applications, we care more about the compression, right? And we compress in 3 different directions, like in the growth direction, perpendicular to the growth direction, so on. Right? So they all increased dramatically compared to the natural wood. For some applications, stiffness is important. Some applications, scratch resistance is important. And sometimes, the impact, this resistance is important. We've done some bullet tests, and we see the densified wood actually can catch the bullet at the different ways. This natural wood, the bullets just pass through it, right? So what this test tells us, we indeed improve the mechanical properties in all aspects. And, this is really come from the structure of these materials. Yeah. From the macroscopic scale, from the large scale, you have these aligned structures, very dense structures without the pores. And it's made of the tubular structures, where the cell wall is closed. So they also form this kind of very good laminate structure, and they are also aligned, right? Like the each tubes now is basically pressed into kind of like a pallet, right? And you have this nanoscale fibers. That's the building block. And each nanofiber itself is made of all these molecular chains. Again, they're aligned. So you have hierarchical alignment from the molecular scale all the way to the macroscopic scale. So that gives you all this mechanical strength and toughness. Yeah, and we believe the strengths come from the removal of defects. This aligned hydrogen bond-based structure gives you this very good toughness. And this process is actually very universal. So that means you can apply this process to different kinds of trees, okay? Either from oak trees, from poplar, from pine, from very cheap, fast growth trees to very expensive, dense trees. And ultimately, all these trees has the very similar building blocks. The difference is mainly in the macroscopic scales. They have some has big pores, some has smaller pores. But after we densify it, they become the same structure. They all dense. The building block is all cellulose nanofibers, and you have lignin inside. So that's basically give you a very universal kind of mechanical behavior. And of course, we really interested in very straight, trees with less leaves. I know Professor Gino is going to talk about the leaves. In this case, we want just the trunk itself, right? And the cost is about $150 per meter cube, and we actually won this RD100 award. So I think the superwood actually can really enable a lot of technology possibilities here. And we are lucky to get the funding from DOE in the United States to work for the car integrations. The idea is very simple, right? When you drive your car, you think about this, your car weighs more than yourself. So when you say, I'm going to drive a car, you are really driving a car. You're not driving yourself. But to save the weight, you really want to drive yourself. But then you don't get the safety. So you want a lightweight car. At the same time, you want to have very good mechanical strength and toughness. So that's the motivation. On average, if you save energy, save the weight by 10%, you can actually increase the energy efficiency about 8%, right? And if you are talking about the flight system, like airplanes, that's even more, right? If you save the weight, you can save more of the fuel and can save more of the cost. And also for the skyscraper buildings. And so this is actually CNBC News. You talk about in Tokyo, they talk about the tallest wooden skyscraper buildings. But the normal wood will not be able to do the job, right? The mechanical strength is only 60 megapascals instead of 600 megapascals. So you have a 10x difference there. So we hope this superwood technology can address a lot of energy efficiency challenges in lightweight materials beyond sustainability. Sustainability was our original, motivation. But I think this material, if we engineer it right, you can actually beat a lot of human-made materials like steel in this case. Okay, so transportation, as I mentioned, for cars, airplanes. It's about 40% of the total energy consumption, right? So you think about it, you are Very often you are on the road, you are taking the train, you are driving your car. That's actually you are spending a lot of, consume a lot of energy. So when you are not a drive, when you are not travel, you are always very often stay inside a building, right? So actually building consumption is about 40%, not 40% of total energy consumption. So I'm going to tell you, how we can engineer wood for building technologies. In this case, we care about the light effect. We care about the thermal comfort, right? How can we see things in the daytime, right? How can we have the best lighting effect? And how can we have the best thermal comfort, right? So if you look at the building, right, and you have windows. A window is a very bad component in terms of energy efficiency, right? But you like a window because they give you visibility, give you comfort and so on. And that's the other major energy leakage. That is your envelope, the walls, right? Either using stainless steel or using some regular wood, that actually don't give you the best thermal protection, right? So again, as I said, it's about 40% of the total energy consumption. So this is a big deal, right? So if we can do anything related to building in terms of energy, in terms of sustainability, that's going to be a very, very important impact. So my group has been working on this kinds of technologies for quite a few years. And the first work was by Mingwei Zhu, was a visiting scholar in my group at that time. We invent this so-called transparent wood. And basically, we remove the lignin that absorb the light, and we fill with some cellulose or polymers to avoid the scattering centers. So you can actually get a very transparent, very low thermal conductivity wood that can actually maintain the optical comfort, but avoid thermal leakage, and it can increase the energy efficiency. We've also done a work called a thermal insulation wood. It's a structural material. In this case, we're talking about a length scale of about 100 nanometers for thermal management. By doing so, we can actually lower the thermal conductivity dramatically. And now this project is funded by DOE BTO office. We're trying to commercialize this technology through invented wood as well. So today I'm going to focus on this so-called radiation cooling wood. Okay, this is a cooling wood that when you put on a roof, it's not going to heat your house even in the hottest summer, but it's going to cool your house because of this radiation effect. Okay, because of the time, I'm going to speak relatively fast for this concept. Okay, so now if you think about this is your house. Okay, this is a building, right? This is the cloud. Okay, and far, far away is the universe. That's actually very cold, right? And then you have the sun, which is very hot. Okay, it's 6,000 Kelvin. So now, let's say if there's no sun, okay, and you should always feel cold because the universe is so cold, right? And if you look at this cloud, you have this transmission windows, and from 8 to 30 microns, you have this very high transmitting windows. And now, let's say your house is a room temperature, say 300 Kelvin, and this is the black body radiation curve. Right? So then this window is transparent, right? So you see that if there's no sun, okay, and your house is going to radiate all the heat through this transparent window, yeah, and you're going to have actually a very cool building, right? Even in the summer. But the problem is actually because of in the summer you have this high flux energy, input from the solar, which is a black body radiation, and it's 6,000. So the center is in range of the visible light, right? So about the cooling your house is really about how can we reduce the heating, the increase the cooling. So overall, you have net output of the energy instead of the input into your building. So we want to make this material white so it doesn't absorb the solar energy. Lignin is a component in the wood which we always don't want. Okay, for now. In the future, maybe we'll want to engineer lignin, but for now, we always want to deal something with lignin. In the previous case, I said we remove some lignin. In this case, we completely remove the lignin. So you see, this is the lignin slurry. It's completely black. It's very black. It's actually a wonderful material. I think there's a lot of potential for this material. Yeah. People haven't really explored yet. But in this case, we're trying to remove it, right? So this is absorption of the lignin, and it's just black, right? That's why, if you put the wood in the roof, it's going to absorb the sun. It's going to heat your house, which is bad from energy efficiency point of view in the summer. So this is actually a completely delignified wood. We demonstrated a few years ago. And you may think this is actually very trivial, and actually to remove the lignin from a very big piece of wood without destroying the structure is actually very, very challenging. There's nothing to hold them together if you remove them, right? Then hydrogen bond formed when you actually drive the water away. And you have to get them apart, but still they're still very porous. Yeah. So it's actually a very, very complicated task. Yeah. And we were, after a lot of effort, we're able to make this kind of a tofu-shaped wood, okay? If you come to my lab, it's really like a big tofu, okay? Very white. It's kind of delicious, actually. It's actually made of completely nanocellulose. And remember, actually, people are putting nanocellulose in food already. And, put 20% of a transparent cellulose in your wood. In this case, we have a white color because we still have a lot of scatterings because of this macroscopic arrangement, right? So now let's look at the spectrum, right? It's very white. It's very obvious, right? And then we measure the reflections. It's actually has a very high haze. It means reflection scattered in all directions. And if you look at the transmittance, of course, it's very white. So the transmittance is actually very, very small, almost zero. And a very, very small absorption as well. So that means, if you put it on a roof, most of the energy will not be transmitted, will not be absorbed, it will be reflected back, right? It has a very high reflectance in the solar energy range from, visible all the way to 2.5 microns. That's what the solar energy spectrum is. So if you do this integral, right, based on the spectrum, you should know how much is the solar absorption if you put this kind of wood in your roof, okay? So it's about 53 watts per meter square. Okay, now look at the infrared. This material is actually completely black. You and I will not believe so because it looks white in the visible. But this material has a lot of, functional groups, has a lot of CO, CH, OH bonds, right? They all vibrate in the infrared. So that means they're going to absorb energy in the infrared. So when you have a very high absorption, that means they're going to have very high emission as well. The absorptivity is the same as the emissivity. So because of that, you're going to have a very large cooling effect, right? So this is the infrared range, okay? And you do the integral from visible all the way to the infrared. It's mainly the infrared range. You get this huge cooling power. The energy goes away, okay, from your roof. So this number is much larger than absorption, which is 53 in the previous slide, right? So now let's add everything together. In the real case, you have convection, you have conduction, and you have actually back radiation from the environment and so on. But by taking this, wide window, this 8 to 13 micron windows, if you do all these things together, you still get a net emission power of about 58 watts, right? So for a 10%, a solar cell, you get about 100 watts for about 8 hours to 10 hours. And this is a 24 hours operation. Yeah. So this is actually even better than most of the solar cells from 24-hour operation point of view. So this work was done through collaboration with Rongwei Yan and Xiaobo Yin from University of Colorado at that time. And we done some real-time tests and confirm the measurement and agree with the calculations and so on. Yeah. So this material, at the end of the day, very different with other radiation cooling materials. The radiation cooling concept really started by Professor Sang Hui from Stanford University using semiconductor structures, and there are quite other interesting works using polymer beads and using multi-layer structures and so on. This material is wood. So intrinsically, it's a structure material. And for buildings, you want the mechanical strength, you want the structure material. So we say that in this case, the mechanical strength is also like 400 megapascals, and it's very much better in terms of scratch resistance. When you use it for the building, you care about the scratch. People is going to scratch it. You have cats. Things like that. Yeah. You care about scratch resistance and the other kinds of mechanical properties as well. Yeah. And this is the specific mechanical strength. Just like before, is also better than lightweight metals. And this material also has very, very beautiful colors, just like pure white. Okay. And I think, this may have applications even beyond this so-called radiation cooling. And we done this building energy efficient calculation through collaboration with Professor Nina Sebrick at the University of Maryland. And the idea, is that, using this material in certain regions, you can save energy about, up to 35%. Okay, for certain areas like those, like Austin, Phoenix, only have a very dry and hot weathers. So this really indicate, if we can engineer this material to play with the optical properties like transparent wood, the thermal properties like insulation wood, or this, like the night and the thermal coupling. You can have this cooling of wood. And this is just one second example. So in addition to superwood, cooling wood, I'm going to give the last example very quickly. It's called ionic wood, okay? Or called nanoionic wood or fluidic wood. It's about wood, using wood to transport ions, transport waters, transport other fluidics in the guided version with a much enhanced speed, with much better regulation. For example, if we make a channel much smaller, we can selectively transport one ion versus the other kind of ions. So you can start to build a charge on one side, and you can also promote the transfer number, for example, in lithium-ion batteries. That is always the key to get the fast charge batteries. So I think, natural wood is doing this every day already. Right? I mean, if you look outside your window, right, you have the trees. They are, right now, they are pumping water, right? They're pumping potassium, sodium ions as nutrients for the trees to grow, right? And they have very interesting hierarchical structures. They have this larger pores, diameter channels, right? And they have this smaller channels, and they have pits on the cell walls and so on. And I think there are a lot of works done for this classical materials. And when we enter this field, we ask this kind of questions, right? So how can we use this nanoscale behavior? For example, in this case, we open them up. We charge the nanofiber apart, so they start to repel each other. You open up the small channels, and you get this so-called nanoionic transport behaviors, right? And remember, this material has a lot of hydroxyl groups. That's the glucose chains, right? So can we modify the structure to make them more surface charged when they, soak in water? They are more likely to be dissociated. So you have more surface charge, negative surface charge. Then they give us a chemical modifications in addition to the physical modifications, right? And we also, hopefully, we can benefit from these hierarchical structures, right? They have this big channel and smaller channels for things such as solar distillation, water distillations. They can transport the water, not the vapor. You can transport this ion, not that ion, and so on. So I give you a very quick example about the solar distillation, right? In this case, the idea is to heat the light onto the surface of the wood. In this case, the wood surface is blackened by carbonization. It's very black, but only on the very top surface. So when the light is heated on the surface, it's going to be absorbed. And because wood has a very poor thermal conductivity, it's porous material, right? So the heat is going to be focused on the surface. The surface will become very hot. The vapor will be formed, right? Will be evaporated. And the water, let's say, under the wood from the ocean, for example, is going to be pumped up through these channels of the wood. So now you have this continuous flux from the seawater to the clean vapor. You can constantly generate clean water using this solar energy. So we done this using wood as well. Just like many other materials, maybe many people don't talk about it, in the beginning. Now people pay more and more attention to this, is that, this kind of device will operate very well, but after a certain time, the salt will start to accumulate, and it's going to make this black material completely white. Then there's no absorption. The channels are blocked. So you have this so-called salt accumulation problem, right? So here we're using this balsa wood. In a balsa wood, they have this bimodular distribution. You have this very large pores, up to hundreds of microns, and you have this very tiny pores like 30 microns. And then in the cell, you have all these piece structures. So the idea here is that on the solar energy heat on the surface, the water will be evaporated through these small channels. The salts will dissolve back through these big channels, and we done some modeling, we do some experiment. We indeed found if you use balsa wood, this bimodular structure can help you resolve this salt accumulation problem. I think this is actually very, very important, from the long-time operation point of view. So that's actually about the big channels, right? And the things become more interesting at the nano size. Okay, I just give you a very quick example. I think this is just the beginning of many, many possibilities. Okay, in this case, you think about, if you have a charged surface, okay, if you immerse it into ionic, salt, like a sodium chloride salt solution, right? So let's say the surface of the wood is electrically charged. It's going to attract the positive ion to the surface, right? They form this so-called double layer with a distance that's about like 1 nanometer for a typical sodium hydroxide solutions, right? So in the traditional wood, the channel is like hundreds of microns. So that's a microscopic region, right? So there's no regulation. Ion transport is just like a transport through a bulk solution. Yeah. The cell wall, the wood wall has nothing to do with it. Okay, now let's say we open up the nano channels. Now the channel diameter is very, very small, a few nanometers, right? So in this case, when the ion is trying to transport through this channel, very small channel, it's just like you trying to go through a very small, aisles with two walls. You're going to be influenced by whatever on the surface of the channel, right? So for example, if you have a negative ion on the surface, it's going to repel the negative ion to go through. Yeah, you're going to attract more of the positive ion to go through. Yeah, so this is so-called nanoelectronics, right? So if you study this kind of behavior, this is what happened here, right? The double layer distance, decreased as you increase the salt concentration. So this is the concentration of the salt. When the concentration is very high, you enter into this linear regime, right? The transport is the same as the bulk solution. There's nothing interesting here. But when you decrease the concentration, or when you increase the concentration, or you decrease the diameter of the channel, you're going to have a much, enhanced conductivity, because the ions inside the channel is going to be always match the surface concentrations, right? So no matter how little ion you have in the bulk, you always have a lot of ions to actually in the channels. So this actually become extremely interesting already. Yeah? And I believe this material can be even more interesting when you go to this molecular scale, yeah, which I don't have time to talk today. Okay, so in this nanofibers, we indeed observe this behavior. This classical behavior is called nanoionic behaviors, right? So this is the, processed cellulose nanofibers, or processed nano wood, okay? And you have this transport behavior, right? This is the nano behavior, this is the bulk behavior, right? As I said, we can even make the surface charge even more by using changing the hydroxide groups to carboxyl groups. So this group is even more easy to be dissociated. So you have more surface charge. So even with the same diameter, you have more surface charge. You have more surface charge on the cell wall. You have more charge in the channel. You have more conductivity, you have higher conductivity. That is so-called, enhancement of conductivity due to the surface charge effect. And to use this kind of behavior, we have to block the big channels. So when you do this kind of experiment, we have two choices. We either densify it, or we either block the channel by infiltrate some polymer into the big channels. So this is a very quick example to show you how we use this kind of nano-ionic behaviors using wood. And remember, the wood is very easy to process here. You can cut them into different shapes, into different angles. So in this case, we can cut wood in this way. The channels are aligned in these directions. And you have what is surface charge, right? So now let's do this device, so-called thermo-ionic electric devices. So you have the temperature gradient. So the temperature is going to drive the positive ion through this negative channel. So the positive ion is going to be here. The negative ion is going to be here. So now you have this voltage build up, right? So you can charge the double layer. You can just like you charge the battery. So if you actually have a redox reaction on both sides, you can actually get a continuous operation, just like a battery. So by using this nano channel, we can get actually record high seebeck coefficient. Because of the very low thermal conductivity, the overall very similar like this seebeck efficiency. The seebeck coefficient is actually very, very high compared to other ionic-based devices. So we can use this wood to harvest energy from low-grade heat, like couple of tens of degrees C. So my group has been working on other technologies. I give you 3 examples: superwood, cooling wood, and ionic wood. And there are many other possibilities like a battery wood, ion-human interface, like Professor Jigan saw last week, gave extremely exciting talks on how to use ions. And maybe the cellulose can serve as an interesting material platform to use for that purpose. And as I said, we have a company called Invent Wood to commercialize these technologies. Invent Wood has licensed all the patents related to these wood technologies and the cellulose technologies. And we also look for potential collaborations through the company. And as I said, we want to go beyond sustainability. I showed you a lot of very exciting, actually, structures with outstanding performances. And remember, wood is old materials, and the people has a lot of knowledge about how to process it, right? In the paper industry, in the lumber industry, right? So, and from the very bottom, you can engineer the seeds, right? You can do genetic engineering. You can plant the wood has more lignin or less lignin, right? So I think there are a lot of possibilities. And now if you use AI, right, to do, images, couple the structures with the properties, the AI can play a very important role to facilitate and speed up the discovery and the manufacturing. So I think there are a lot of possibilities here. So this is actually slides, the video from Nature. Just shared. This is accessible from YouTube. So in the future, a sustainable future will need the use of this sustainable materials. So the question is, do we have enough materials, right? And this is a video I'll let you watch.
How many trees are there in a forest? What about a country? How about in the whole world? The answer, we now know, is that our planet is home to 3.04 trillion trees.
So on average, we have about 400 trees worldwide. And so I think that's really enough material for us to play with. So with that, I would like to acknowledge my students. The superwood is really developed by Jian Wei and Zhao Ji, and together through collaboration with Professor Tenni's group. The cooling wood is done by Tian Li. She's going to be a professor in Purdue University. And with Shuai Ming, through collaboration with Xiaobo and Rongwei. And the ionic wood we done is again by Tian Li, and through collaboration with NIST, Dr. Rob Reiber's groups and so on. Yeah. We also acknowledge some other collaborators and so on. Thank you so much for your attention.
Wow, great. Liangbing, really, really great talk. Yeah, I enjoy very much for this magic wood. You really make a lot of things, out of my imaginations. So yeah, could you please close the share screen? Then we can go to the question part. A lot of people was online waiting for your answers. Yeah. Okay, great. Yeah, so let's see. We have many questions from different places. Yeah. The first question is Lily from Beijing. Thank you, Professor Hu. One question is, wood is a great element, but it is hard to integrate with other materials to enhance the performance. How to overcome this problem or limitations?
Integration is always a challenge, yeah. And so ultimately, wood is a soft material. So, I mean, when you integrate, there are different ways to integrate. I mean, mechanically, it's soft, so you can just mechanically join them together, yeah, right? Or you can shape them, by cutting into shapes, and then you can lock them together, right? Or you can use glues, right? And yeah, you are right. Because wood, traditional wood has a lot of pores. You can use glue easier. For the superwood, it's so dense, so flat. You do have challenges here, but I don't think that. I mean, people are smart. Yeah, there are always solutions. Yeah, as long as it's a good material, I think.
For sure, it is. You already made such a big progress. I think later, many technologies can come in and make some kind of magic. Then the second question is Professor Hu. Very impressive talk. For the super light wood, can it be mass production? How about the cost? I think this one must more curious for the commercialization of this light.
Yeah. So so Invent Wood is doing this manufacturing and commercialization effort. We have a project funded by DOE, and I think one of the major motivation for using wood nanomaterial is because its potential advantage in mass production. Mm-hmm. You think about the other nanomaterials. I work a lot on carbon nanotubes here. You have to first. You have to synthesize this material first, and followed by purification, and then scale up and so on. And this material you don't need to fabricate. You just plant the seed, yeah. And Alice was yesterday, her bamboo in front of her house, right? Alice, you said your bamboo can grow 1 meter per day, right? Bamboo can grow very fast, yeah. So I think mass production shouldn't be a problem in the long run. It may take time, yeah, but I think it's in the right direction. And the cost, we done some estimate there. It's going to be cheaper than the material we're going to compete here, such as steel, right? Of course, it's going to be more expensive than wood. But again, if you compare with wood, the price vary a lot. You have very expensive wood that takes hundreds of years to grow.
Right? That's right.
Like a honmu, right? It takes a long time to grow. Yeah. But remember, the process we're doing here, we can start with very cheap, fast growth wood. They only take 3 years to grow. After densification, this wood is even better than honmu, okay? Then the best dense wood, you can, why it's expensive? Because it takes a long time to grow, yeah. Why it takes well, because of the structure is very dense. So now by doing this process, actually we speed up the manufacturing by nature, right? So, and I would like to point out that the things we present right now are for wood, right? But these knowledges can be used for bamboos, can be used for many other biomass materials. I think it's really, the broad impact shouldn't be limited to one kind of wood or one kind, we should really think about how can we use nature materials to really, and at the same time, take serious consideration of manufacture as a key aspect. Thank you.
Yeah, it is really, really interesting. I also interested in this part too, because there are many kind of factories already there. So if you can merge your new technology with the traditional one, that may be mass production costs can be also get low down. Yeah. So it's very good. Yeah, so we go the third one from Yuri. Yuri was Gogotish. He's very excited for your magic talk. He's enjoying the talk. So the question is to you, would be the limitations? Yeah, no material is perfect. Yeah, can we really replace all structured metal sheets with densified wood? If not, what does prevent?
Yeah, thank you, Yuri. A very good question. I'm very glad that you are in the audience. Thank you. And question, yeah, wood definitely has a lot of problems, to prevent for a broad range of applications. Wood, plastic and metals, they can be formed easily by, extrusion or casting, right? They can make it into different shapes and form it very easily. And the wood is more like a thermosetting material. Yeah? You cannot, punch it into a shape, right? And that will only break it, right? So I think that's one of the major limitations, and that's actually a mechanical issue. I collaborate a lot with Tenny, and we face this limitation all the time. Yeah. So hopefully our next breakthrough will be about this.
Okay, because Yuri has been asked by Professor Zhigang Su, don't ask for what you Maxine can do for you, ask what you can do for Maxine. Yeah, so maybe you also can answer like this. Don't ask what the limitation for this. Ask what you can do for wood.
Yeah, I think definitely right. Every material has limitations, and yeah, thank you.
It is. The next one is one from Nanjing Agriculture University, Professor Ku. Thank you for your fantastic talk. You really make magic wood, much more than our imagination. My question is it possible to make all kind of wood biotechnology, or just a few selected kind of wood? Yeah.
So, the more we're working with this material, the more as we're facing new challenges, and we find a lot of opportunities here. It's just like a people, right? Every people is different. Every tree is different. Even the same kind of a tree, if they plant in different distance, okay, let's say if the tree plant like this distance or that distance, as the distance increase, okay, the tree will actually grow faster. They will not compete nutrition sunlight anymore, right? So actually, if you look at the microstructure, the cell walls, cells are much bigger, and the rings are much larger, and the speed is much faster. Yeah? So, and there's when we work for technologies, always there's a structure property relationship, right? So if the structure is different, the property will be different. Yeah? And the technology associated with the property will be very, very different. For example, just give you one example. Yeah? And then we talk about the solar distillation, right? Using the balsa wood, we can remove the salt because this is a bimodular structure. You have the big channels, you have smaller channels. If you use pine, they have more uniform distribution with the channels. You won't be able to do that. Yeah. So, I think that's why I think in the potential future, in the future, because there are so many kinds of trees, right? They all depends on the weather, right? And so on. I think the AI, artificial intelligence, may help us sort out this relationship more quickly. And the people start to bring this concept up already. And then, now what, right? So let's say if I really want this kind of tree, right? You can plant this kind of tree with a well-planned distance and so on, right? You can either do gene engineering, you can do genetic modification, right? So I think there are a lot of possibilities. And, we are from, I'm from material science department, and, you will work on nanomaterials. And, there are a lot of people actually working for wood, like plant scientists, plant science, right? And they're working on gene engineering. If we work together, I think there will be a lot of new opportunities. Yeah. And
I do think so. After this talk, I think you will get many invitations from the agricultural plant department because you really open a new window, for them. Like he said that's really out of imagination. Normally the people working in this side, they didn't think, in this way can get nanotechnology involved with traditional wood. That's a very good, start. Let's keep on going.
I would say I personally benefited from this a lot already, and I don't know anything about the wood. I say 6 years ago, and I learned this a lot with visiting students, business scholars, collaborators. They are my handbook for wood structures, chemistry and so on. And I think Alice, you are definitely right. Yeah, we need to work together from completely different disciplines. Right? In this kind of collaboration, we can really come out from our comfort zone and be shocked by new fields, and then come out with interfacial ideas. The ideas that come only at the interface. Yeah.
It is right. That's why I can ask the talks. Invite so many different, scientists from different fields. We exchange ideas, get like the brainstorm. Get some new idea came in. Come out the comfort zone to see something new. Okay, we still have one more question. That's a pretty long question. Zhang Yi from NTU. Where primates and technology? What's the environmental impact of the chemical treatment? How is pollution compared to the paper making, which generated heavy pollutions? So then the second part. Okay, you can answer the first part.
Okay, so that's a wonderful question. I really don't like chemistry because my training is on physics, so now I have to deal with a lot of chemistry. I read a lot of books and so on. But I don't have too much insight on this. But I know that the paper industry is making a lot of progress. Making tremendous progress. Now the current paper industry, paper mills, the manufacturing plants are completely different with many years ago, right? So there are different kind of standards. It's really about regulation and the standard, right? If you have a standard, if you regulate the standard, and the people will follow, and this pollution problem can be dealt with, right? Mm-hmm. So I think I think we have enough understanding and knowledge about how to avoid the high dose use of those sulfide-based chemistries, and if you do this very careful, recycling, you can deal with that. I mean, I work on batteries a lot. I visited some battery plants. You would think you're going to use a lot of organic solvent and so on, such as NMP. It can be fully recycled, and they have zero waste. I visited some battery plants before. It's wonderful. Yeah, I don't know. I answer your questions, but the chemistry we're using, you are right. The chemistry we're using are not new chemistries. We're using old chemistries, but we're using in a very careful way so that we can get the structure we want. So the idea for us to move forward is to integrate the existing infrastructure of how people deal with waste. Second question.
Okay, then we go to the second part of this question. A lot of ancient China agriculture architectures are made of wood. Dimension stability and fire, retardance are always a problem. How would you densify wood make a difference? And that's a very good point.
Yeah, again, very good question. Yeah. I think dimensional stability and the fire retardance will be improved for the same reason. And let's say if you talk about the superwood, right? Fire propagate faster because you hold this pores inside, right? Ultimately, the superwood will be burned. If you put it in the wood in the fire after a long time, it's going to be burned. But the fire retardance is going to improve dramatically. We have a publication last year by that through collaboration with the fire protection department, and that's actually a department in our university the rank very high because they focus on the file resistance studies. Dimension stability, I think is the same thing, because now you don't have this pore structure. You would have better dimension stability. But I do need to point out, the water is the major enemy for cellulose. So for the coatings functionalizations into certain depths of wood is going to be important. You see those electrical poles, right? 电线杆, right? They can. I was always wonder. I mean, they use that for a very dangerous purpose. I mean, if they fall, it's going to be disaster. Yeah. But if they corrode over time, yeah. But it seems like people have very good solution for avoid preventing this corrosion and dimension stability by infiltration some chemicals inside.
Okay, great. Yeah, thank you for a wonderful talk. Yeah, I think we have the question. Okay. Oh my God, we have one more. Yeah. So Yan Niu from Xi'an Jiaotong University, Professor Wu, thanks a lot for your wonderful talk. What's the advantage of wood material for flexible electronics and wearable devices compared with hydrogel? Yeah, last week was hydrogel.
Yeah, I think they cellulose can make it into a hydrogel as well. Yeah. I mean, a lot of people using cellulose instead of polymers to make a hydrogel, and because they are very long and they can be surface functionalized, and hydroxyl groups love water, and I think they can be a new family member for hydrogel technologies, and I think we should work together. Flexible electronics very often is about printing. Like if you talk about the process, yeah. So flexibility allows you to do rotary printing, yeah. And the paper is a very good printing material because it can really absorb the solvent because of the porous structure, yeah. So we have done a lot of work before for flexible electronics, just because in US this flexible electronics area is not as popular as in Asia countries. Yeah. So I think Alice, you asked it last time. Nobody is asking this question. Why I'm working on wood? I hope to use this to answer, if you don't mind.
Sure. Yeah. Okay. We have time to discuss on that. Okay. Yeah. Okay. Now I will give you certification for this wonderful talk. ICANX tax tradition. Because on this ICANX tax, we really want invited the top scientists, share the latest, results and technologies, connect the world and the universe. Let everyone know, all this technology was going to change the world. So Liangbing, that's for you, the electrical version.
Thank you so much. Very honored to present along with the most distinguished scientists in the world. Yeah. Thank you.
Okay, great.